All right, let's dive right into a really cool biomedical engineering challenge. We're going to figure out how we can possibly listen in on the super faint electrical signals that are constantly firing inside the human body. We're talking about designing biopotential amplifiers, the absolute key to capturing things like an ECG or an EEG. So let's get to it and engineer a solution from the ground up.
So, to really get a feel for the problem we're up against, just think about this question. That tiny, critical biological signal we're trying to measure, that's the whisper. And the hurricane? Well, that's all the overwhelming electrical noise coming from inside our bodies and just from the world around us. Our entire job as engineers is to build a circuit that can somehow pick out that whisper perfectly, while totally ignoring the hurricane that's just raging all around it.
So here's our game plan. First, we're going to really define the challenge we're facing with these biopotential signals. Then, we'll walk through why your basic off-the-shelf amplifiers completely fail at this task. After that, we'll uncover the secret sauce for noise rejection, a concept called CMRR. That's going to lead us straight to the gold standard solution, the instrumentation amplifier. And finally, we'll zoom out and see how this amazing little component fits into a complete, real-world medical device.
Okay, let's get right to the core of the problem. As the slide says, we are dealing with a situation of millivolts versus volts. What that really means is we are hunting for these incredibly tiny, medically important signals that are literally thousands, sometimes even millions of times smaller than the electrical noise that's drowning them out. It's pretty much the ultimate signal-to-noise puzzle.
And this slide right here just perfectly shows you the insane difference in scale we're fighting. Look on the left. Our signals, like an ECG from the heart, are in the millivolt range. An EEG from the brain, even smaller, way down in the microvolts. But then you look to the right. The interference we have to reject, mostly from what's called the DC electrode offset potential, can be in the range of whole volts. That is 1,000 to 1,000,000 times bigger than the signal we actually care about.
And seriously, this is no joke. A really important paper from Spinoli and his colleagues confirms it. The noise is several orders of magnitude larger. What they're talking about is this DC electrode offset potential. It's basically just a steady, unwanted voltage that gets created from the simple chemical reaction between the metal electrode and the conductive gel we put on the skin. And this DC voltage, it's the first and, honestly, the biggest wall we have to get over.
Okay, so we know the problem. Now let's put on our engineering hats and actually try to solve it. We're going to walk through a couple of ideas that seem logical at first, but are actually deeply flawed. You know, understanding why these first attempts blow up is the best way to really appreciate why the final solution is so clever.
So the first thing you might think of is, okay, the signal is tiny, so let's just grab a standard op-amp and crank up the gain to make it bigger, right? Seems simple enough. But yeah, this idea hits a brick wall almost instantly.
And this picture shows you exactly why it fails. Remember that huge DC offset we just talked about? Well, a simple amplifier just amplifies everything. So if you have a 1-volt DC offset and you set a gain of, say, 1,000, the amplifier is going to try to output 1,000 volts. Of course, it can't do that. It just slams into its power supply voltage and gets stuck there. We call that saturation. And as you can see, our poor little biopotential signal is completely chopped off, totally lost. The amplifier is completely maxed out, just trying to deal with that DC noise.
Okay, attempt number 2. The big DC voltage is the problem, so the next logical step is, let's get rid of it. The classic electrical engineering trick to block DC while letting AC signals through is to use capacitors. We call this AC coupling. It's a much smarter idea for sure, but it actually ends up creating a brand new and much sneakier problem.
So we put capacitors in line with the inputs, and that successfully blocks the DC offset. Great. But here's the catch. Op-amps need a tiny, tiny trickle of current to work, called bias current. To give that current a path to ground, we have to add resistors. And this is the trap. For a differential amplifier to do its job, its two inputs have to be perfectly balanced. And the tiny mismatches that are unavoidable between these two new resistors, well, they create an imbalance. And that imbalance just destroys the amplifier's ability to reject noise. So we've solved one problem, only to make ourselves completely defenseless against all the other noise. And this brings us to the absolute heart of the matter, the core concept in all of biopotential amplifier design, common mode rejection. This is the magic property that lets us finally ignore that hurricane of noise and zoom in on the whisper of the actual signal.
So what exactly is the common mode rejection ratio, or CMRR?
Well, think of it as a report card. It's a single number that tells you how good an amplifier is at doing two things at the exact same time. Amplifying the difference between its two inputs, that's our signal, while completely rejecting any signal that shows up on both inputs at once, that's our noise.
And the circuit that makes this happen is the differential amplifier, which you can see right here. Instead of just measuring one signal compared to ground, it looks at two signals, say from two different electrodes on your chest, and it only amplifies the tiny voltage difference between them. This is so powerful because any noise, like that annoying 60 Hz hum from all the power lines in the walls, gets picked up by both electrodes pretty much equally. The amplifier sees that as a common mode signal and just ignores it.
This table just spells it out perfectly. The differential signal, our precious ECG, it gets a high gain. Awesome. The common mode signal, all that unwanted noise, gets a gain of basically zero. It gets rejected. That is the magic trick of differential amplification. A high CMRR just means the amplifier is a genius at telling these two types of signals apart.
And we're not talking about just a little bit of rejection. A typical requirement for a medical-grade ECG amplifier is a CMRR of over 100 decibels. Now, to put that in perspective, that means the amplifier is at least 100,000 times better at amplifying our signal than it is at amplifying the noise. That's the kind of performance we absolutely have to have.
Okay, so now we have all the requirements. We know we need to block DC, we need a lot of gain, and we need a ridiculously high CMRR. And that brings us to the final design, the elegant solution that solves all of these problems at once, the instrumentation amplifier.
Now, you might be wondering, if that simple 1 op-amp circuit we saw a minute ago gives us that great CMRR, why don't we just use that? What's the final piece of the puzzle that's still missing to make it work for signals coming from the human body?
The answer is two words: high input impedance. The idea is actually pretty simple. If your measurement device tries to pull too much current from whatever it's measuring, it actually changes the voltage it's trying to read. High input impedance means the amplifier basically doesn't draw any current. It just looks at the voltage without disturbing it, letting us get a true and accurate measurement. That simple differential amp just doesn't have a high enough input impedance for a delicate job like this.
And here it is, the classic 3 op-amp instrumentation amplifier. This beauty is the grand finale of our whole design process. It is specifically built to give us all three things we need: high gain for our tiny signals, that super high CMRR to kill the noise, and an incredibly high input impedance so we can connect to the body without messing up the signal.
So let's quickly break down how this thing works. The first stage, right at the input, is made of 2 op-amps that act as buffers. Their main job is to provide that all-important high input impedance. They also give us our first bit of gain. Then, stage 2 is really just that single resistor that's shared between them, which is a really clever way to let us easily set the overall gain. And finally, the third stage is just our old friend, the differential amplifier, whose only job is to subtract the two signals and provide that last powerful punch of common mode rejection.
So we've done it, we've engineered our perfect amplifier. But you know, in the real world, this component doesn't just live on its own. We need to zoom out and see how it fits into the complete system for measuring biopotentials.
And this block diagram shows it all. Our instrumentation amplifier is absolutely the heart of the system, but it's just one piece of a bigger puzzle. Before this signal even gets to our amp, it has to come from electrodes on the skin, and after our amp, it has to go through filters to clean up any leftover noise and limit the bandwidth. And most importantly, there are safety isolation circuits to make absolutely sure the patient is protected from any possible electrical problems. It's a whole system working together. And the design of that whole system really depends on what signal you're trying to measure. Just look at this table. An EEG signal from the brain is way smaller and has a much lower frequency than an ECG from the heart. That means an EEG amplifier is going to need way more gain and totally different filter settings than an ECG amplifier. There's no one-size-fits-all solution. The design has to be tailored specifically for the signal you want to capture. So we've successfully engineered a system to pull that clean, clear whisper out of a raging hurricane. We've got the waveform, but that just leads us to the final and maybe most important question. Now that we have the signal, what comes next? What are the new engineering challenges in signal processing and machine learning that let us actually interpret these complex patterns and turn them into a real diagnosis that can improve someone's health? That's where hardware design meets data science, and that's a whole other story.